Okay, good morning all. So in the last class we looked at digital signatures and their differences with the symmetric key-based message authentication methods. So today I'll give a quick revision of the digital signatures, and then we'll look at the public key certification. In other words, the certificate authorities who certifies one's public keys. And then we're going to look at the tutorial 5 questions. And then perhaps if the time allows, we will be looking at the live authentication problem. So let's remember the digital signatures. So the purpose of this is to provide assurances that the message in fact comes from the claimed source and that it hasn't been modified, tampered with, in transit, right? So here, the sender needs to attach something of its own to the message, and that is our private key. Let's turn this on. Okay. So here is our message. We first take the digest of the message. It serves two purposes. First of all, even if your message is too large, you can reduce it to a fixed size 256 bits or so digest. And then the other purpose is that without that hash function, it doesn't work, in fact. It ensures the security. But that's a different discussion. It's not within the topic of this class. And then we apply our private key by means of encrypting the digest. And then this is our signature for the message M. But we don't only send this because there is no way the receiver can obtain the message from its digest, right? So we send M together with this. So M together with the signature. And then at the receiver side, the receiver takes the message and takes the signature. And the receiver applies hash function to the message, so she also obtains the digest of M. And then for the signature, she applies the public key of the sender. And we know for a fact that when you apply the public and private key, the key pairs subsequently to the same bit sequence, in this case that is H of M, you can obtain the same bit sequence, which is H of M. And then she checks if these two are equal. And if they are equal, she knows for sure that the message originated from Bob and that it hasn't been modified in transit. So this is digital signatures. We also said that it serves a similar purpose with the symmetric key message integrity schemes, like the message authentication codes, but certain differences as to what key you use. Here you use your private key. In the symmetric key-based method, you have to use your shared symmetric key. Therefore, you need to establish keys first. Here, you don't need to do that. And because it is something of your own and only you can sign it, your receiver can later prove, or anyone for that matter, can prove that you have indeed sent that message and you cannot deny it, and this is non-repudiation. But still, even if you use digital signatures, there is something that your receiver needs to know, and that is your public key, right? Your receiver verified your signature using your public key. And yes, we assume public key is publicly known. Yes, you can distribute it to everyone. You can perhaps advertise it in your website. But how does your receiver get the public key with message authentication and integrity? In other words, once you send that public key to your receiver, how do you ensure the integrity of that message in the first place? That is still a problem, an issue we need to discuss. And for that purpose, we have public key certification. So before that, let's see an example of what can go wrong in public key verification, in a digital signature verification scenario. So here in our example, Trudy is our malicious adversary, or the malicious attacker, wants to play a prank on Bob, and Alice is the pizza person. She's cooking pizza. She has a pizza store, and Bob wants to order pizza. Bob doesn't order pizza, but Trudy can order pizza on behalf of Bob, even if that message did not originate from Bob. So let's see what happens. So Trudy creates this email order saying that, dear pizza store, please deliver to me 4 pepperoni pizzas. Thank you, Bob. So she wants to impersonate Bob. So Alice will receive this message, but in addition to the message, Trudy attaches a digital signature. So Trudy signs that order with her private key. Let's say her private key is K of T minus, okay? But she claims that this is Bob's, she claims that KT plus is indeed Bob's public key. So Trudy sends the order to the pizza store, and Trudy sends to pizza store her public key, which is KT plus, but claims that it is in fact Bob's public key. So let's say the claim is that this is in fact KB plus. But if you do not use a message authentication method in sending your public key, the receiver has no way of verifying that this is indeed Bob's public key. And then the pizza store can verify the signature because, you can verify any signature signed with KT minus using KT plus. And because the verification goes through, the pizza store doesn't suspect from anything, and Alice delivers 4 pepperoni pizzas to Bob. But Bob may not even like pepperoni pizzas. So an important application in digital signatures is the public key certification, which certifies that a public key belongs to a particular entity, particular identity. And it is being used all over the network protocols, such as the transport layer security in the web. So this is a little more technical detail as to what happens. So Trudy writes this message and claims it is from Bob. She applies a many-to-one hash function. This is our first step in signature, right? And then she encrypts that digest with her private key, KT minus. So this is what she obtains, KT minus of H of M. And this is the signature. She sends this along with the message itself. And when you apply Trudy's public key to that digest, to that signature, Bob will obtain H of M. Alice will obtain H of M, and she will also check if this H of M is equal to the hash of this message. And it will match because Trudy claimed that this is Bob's public key, and Alice shall use it when she needs to verify the signature. So how to fix it? Using public key certification, if we certify that this public key is in fact Bob's public key, then the pizza store can ensure that this message is indeed coming from Bob. So we have something called the certification authority or certificate authority, or simply CA for that. It binds the public key to a particular entity. So it's just like saying, my name is Utku, and I have a public key of this, and this is certified by some other authority by means of signing that binding. So it's just like this. So here is Utku, and here is his public key, and I sign this using some certificate authorities private key. And this fact, the fact that KU plus belongs to me, can be certified by the private key of by using the certificate authority's own signature. So this is how that registration works. Let's say a person or a router, some entity or a web server wants to register the public key with the certificate authority. First, he needs to provide the proof of identity. I need to prove that I am indeed Utku. Perhaps I can send my government ID or something. And then if the certificate ID is convinced about that link, the fact that I am indeed Utku, then it will create a binding to my public key. So I sent my identity, and I sent a public key, which I want to use, and the certificate authority binds that by means of signing it. So let's say this is Bob here, another example. Bob's identifying information. Bob also chooses a public key, sends that to the certificate authority, CA here, and the certificate authority signs that using its own private key. So in the end, what happens is that you have the hash of Bob's ID and Bob's public key. This is encrypted with the certificate authority's private key. Yeah. So this is how a certificate looks like. And then Bob can share this certificate with anyone who wants to verify Bob's signatures, so that they can first extract Bob's public key out of this and verify it. Now that they are certain that Bob's public key is this, KB+, then they can go ahead and verify any signature created by Bob. And this is what happens. Now, let's say Alice wants Bob's public key. She gets Bob's certificate. So this certificate is just what I wrote here. Well, she can get it from Bob himself, or she can get it directly from the certificate authority. It doesn't matter where you get it from, because once that certificate authority signs it, it is the proof that, in fact, this is Bob's public key. And then she will apply the certificate authority's public key to verify that signature, right? So in order to verify this, what do you need? You need the certificate authority's public key. In other words, you need to apply KCA plus to this so that you can obtain whatever's inside, and then you hash Bob's ID and Bob's public key to see if that is equal to what's there in the rectangle. Hash of Bob's ID and KB+. So let's say this is the CA's public key, and this is the certificate. Alice will encrypt the certificate with the CA's public key, and then she will obtain the hash of Bob's ID and Bob's public key, and then from there she can check when hashing Bob's ID and KB plus whether she can get to the same digest. And if she can get to that, that means that certificate is authentic, and Bob's public key is KB plus. But then this might cause another problem to arise here. How do we know the certificate authority's public key? So yes, now we can obtain Bob's public key from the CA, but how do we know in the first place the certificate authority's public key to verify a signature signed by a signature created by the certificate authority? Right? Well, the answer to that is just you somehow know. So there are a few known certificate authorities. Maybe let me explain that over a drawing. Oh. Okay. So similar to DNS, there is some hierarchy in the certificate authorities, and there is a root certificate authority. And this root certificate authority has its own private and public keys. Let's denote them by k root of plus and k root of minus. Plus for the public key, minus for the private key. And the browser codes in themselves have kr plus. Let's say this is your browser, and you're doing web browsing, so you want to connect many websites around. And before, of course, establishing secure connection with the websites, you need to obtain the public key of the websites so that you can verify their signatures. And your browser, whenever you download your browser, inside that, it contains all the public keys of the root certificate authorities. There are not so many, so you can store them. And under these root certificate authorities, there are many certificate authority companies. These are usually trusted companies. For instance, some of them can be Google, can be Symantec, can be Norton. It can be cybersecurity companies specifically doing this, or it can be a larger company doing this as a part of their business. But let's say there is CA1, there is CA2 here, there is CA3 here. And each of these, let's focus on CA1 for the time being, each of these will obviously have their own public and private key pairs. Let's say K1 plus and K1 minus for the certificate authority 1, right? So your browser, once you download it, will not know all these companies and their public keys, so you don't know their identities. Even if they send you, here is K1 plus, here is certificate authority 1's public key, you cannot trust it because you do not have proof that it is K1 plus's public key. But let's say now you want to connect to a web server. Let's say you connect to Alice's web server, all right? And Alice has her own private and public key pairs. And let's say that Alice uses certificate authority 1 as her certificate authority. So she will send you her public key certified by CA1. And what is that? So Alice will send you her, let's write a little bit towards the right. So this is your browser. So she will send you her public key and her ID together, signed by K1. Oops, that is K1 minus. In other words, this is the certificate of Alice, certified by CA1. So let's say you receive this. You receive the certificate of Alice certified by K1 minus. But your browser only knows the public key of the root certificate authority. So what it does is that it contacts, your browser contacts the root certificate authority, and you usually obtain the IP address of the root CA. I'm sorry, you do not contact the root certificate authority. You contact the CA1 to see what root certificate authority it uses. In that case, this is KR minus. And you also obtain that certificate signed by the root certificate authority, certifying that certificate authority 1's public key is this. So your browser then contacts CA1, and then CA1 will send you their certificate CA1 KR plus K1 plus. Right, so this is the signature generated by the root certificate authority binding this public key to this certificate authority 1. You can verify this using KR plus, right? Your browser already knows KR plus. So after verifying that, you will be certain of this binding. And now that you know K1 plus, you can verify this signature and establish that Alice indeed has KA plus as her public key. Is that all clear? Do you want me to repeat? Anyone? Okay. So this is about certificate authorities, and we have them all over. Wherever we use public keys, we first obtain the public keys from a certificate authority, because there is no other reliable way of obtaining it before verifying someone's signature. Okay. So next we have endpoint authentication. So this is also for the liveliness of the communication. This is to ensure that the other party is also alive during the communication, and you are also ensuring that you are communicating with that party when they are alive. There is no message, but you usually do endpoint authentication prior to sending any messages. But I think, so let's do the tutorial first, and then if the time allows, we can do endpoint authentication. Because I'm not sure if we are going to have enough time after doing the tutorial for this. Any questions on the public key certification? No questions? All right. Okay. Okay, so the first question is about video reception and playout delays in video. So video is encoded at a fixed bit rate, and it is also sent at a fixed bit rate, meaning it can be, for instance, UDP. We don't have prefetching of the video. We do not receive video frames faster than they are encoded. And they are sent by the server at time T0, and they are received at the client side starting from T1. And the playout delay can occur at T1, or the playout can occur at T1, or it can occur later if we introduce some playout delay. All right? So the server transmits the first video block at T0, the second block at T0 plus delta, the third block at T0 plus 2 delta, and so on. And once the client begins playout, each block should be played in delta intervals. So A, suppose that the client begins playout as soon as the first block arrives at T1. How many blocks of video will have arrived at the client in time for their playout? So because a block is played in delta times, all we need is to, draw these steps starting from T1. Just being careful here to draw to scale. Okay. And then we are going to count the instances where the corners of the red are before the blue line, and claim that these cannot be played because at the time they have to be played, the video block has not yet been received. So let's see. So this is played because it was received right when it was supposed to be played. This one was not received at the time it has to be played, right? I'm looking at these times, these points. So this is, oops. This is also not received in time. This is received because the blue line came first. The blue plot came first. Same as this. Same as this. And for the last one, it also hasn't been received because the time it is received is here, whereas it had to be played earlier. So if you look at this, the first frame is received, the first block is received, fourth block is received, fifth block and sixth block are received. So that is in total 4 checks, right? 1, 2, 3, 4, yeah. So 4 blocks have arrived in time for their playout. So in B, suppose that the client begins playout at T1 plus delta. How many blocks of video, including the first block, will have arrived at the client in time for their playout? Okay, so let's zoom in again. Let's use a different color. So now we are going to begin playout at this time, delta time later. So again, I'm drawing the same very carefully. Okay. Now we need to count the instances where the blue line was on the left or right on top of the yellow line, and the instances where the blue line is on the right side of the yellow line, meaning that video has not arrived in time for playout. Let's use maybe another color for that. I think this will do. Okay, so here it arrived on time, right? The blue line is on the left. Here the blue line is on the left. Here also. Here also. Here also it's left. It's also on the left here. But here, on the other hand, the blue line is here, so it arrived later, so it cannot be played. So only the last one was not played. How many times it can be played in time? 1, 2, 3, 4, 5, 6 times. Right? So in C, in the same scenario at B above, what is the largest number of blocks that is ever stored in the client buffer awaiting playout? Okay. So we need to count that. Okay. So at this time, at T1 plus delta, we only have this frame in the buffer, the first frame in the buffer. Because the second frame, the moment it comes, the first frame is played, so we only have one at the buffer. So I'm going to write 1 here. What's going on? Yeah. So if you look at T1 plus 2 delta, I have received 2 frames so far, and I played 1. So I also have 1 frame in the buffer here, or 1 block in the buffer here. Let's look at the next one, the T1 plus 3 delta. Well, I played 2 frames, but I received 3 frames, so I also have 1 frame in the buffer here. So for the next one, T1 plus 4 delta, now let's see. I have 1, 2, 3, 4, 5, 6 frames received so far, but I only played 4 frames. 1, 2, 3, 4. So I have 2 frames in the buffer, or 2 blocks in the buffer here. In T1 plus 5 delta, well, I played 1 frame, but I also received another frame, so I also have 2 here. If you look at the next one, again, let's count how many we received. We received 6, 7 frames so far. And we played 1, 2, 3, 4, 5, 6 frames so far. So I have just 1 in the buffer. And for the last one, I don't have anything in the buffer. I cannot even play it in time. So at most, the largest number I have is 2. So it was already asking the largest number of blocks that is ever stored in the client buffer awaiting playout. That is 2. And now we are looking at the smallest playout delay at the client such that every video block has arrived in time for its playout. So we need to draw the same step-by-step plot so that all the frames, all the blocks can be played in time. Maybe use this color. Right. So the only block that couldn't be played in question B was the last block, right? So for me to play the last block, my playout for the last block should be later than it was arrived. So I must play it here on the right top. So if I work backwards from here, I'm going to get the right playout. Okay, so I need to start my playout here, which is T1 plus 3 delta. So that means my playout delay has to be 3 deltas. All right, any questions? Okay. So then I'm moving on to the second question. So here we have a leaky bucket, and we have also a queue before that leaky bucket. And we have some packets arriving. Let's read the question quickly. Bucket filter is being fed by a stream of packets. The token buffer can hold at most 2 tokens, so B is 2. And it is initially full at t equals 0, so it starts with 2 tokens. And new tokens arrive at a rate of 1 token per slot, so my R is 1 token per slot here. The output link speed is such that if 2 packets obtain tokens at the beginning of the time slot, they can both go to the output link in the same slot. The timing details of the system are as follows. So my output has unlimited rate as much as my token filter allows. If I have 2 tokens, I can let out 2 packets at once. If I don't have any tokens, I won't be letting out any packets. So this gives me the timing of what happens in the system. So first thing that happens is that packets arrive. For instance, at t equals 0, these 3 packets are arriving, packets 1, 2, 3. If there are already packets in the queue, then the arriving packets join the end of the queue. So this is a first in, first out type of queue, no priorities whatsoever. And after the arrivals have been added to the queue, if there are any queued packets, 1 or 2 of those packets, depending on the number of tokens available, will each remove a token from the token buffer and go to the output link during that slot. So in the example here, because packets 1 and 2 will be in the packet queue in time slot 0, they will both remove the existing tokens and they will be at the output. So 3, a new token is added to the token buffer if it is not full, since the token generation rate is R equals 1. This is what we already know from leaky buckets. And a time then advances to the next time slot, and these steps repeat. So this gives me the order of what happens in the system. And this is just like an ordinary token bucket with a capacity of 2 and a token arrival rate of R equals 1. And we also have a first in, first out filter here. So now we need to answer these 2 questions. For each time slot, identify the packets that are in the queue. The packets that are in the queue and the number of tokens in the bucket immediately after the arrivals have been processed. So what that means is we first process these 3 arrivals. So, I have packet 1 here, packet 2 here, and packet 3 here. After I process this, but before any of the packets pass through the queue, that means I will still have 2 tokens when I'm recording the number of tokens, because this is asking me to record the number of tokens after the arrivals have been processed, but before any of the packets have passed through the queue and removed a token, before tokens are removed. So at time equals 0, I'm going to have 3 packets in the queue, and I'm going to have 2 tokens in the bucket, waiting to remove these packets. Okay? And in the second question, for each time slot, indicate which packets appear on the output after the tokens have been removed from the queue. So which packets appear at the output, but this is after the tokens have been removed from the queue. Okay? So following the same example, because I have 2 tokens here, it's going to remove packets 1 and 2, and I'm going to have packets 1 and 2 in the output. So for that, let's make a table here to answer both questions at once. Okay. So here I'm going to put the time slot, T. So what were the questions? The packets that are in the queue. So this is going to be my queue, packets in the queue. This is going to be the number of tokens in the bucket. And the last one will be which packets appear on the output. So this is going to be the packets in the output, but that is after they are processed by the bucket. Okay? So let's write down the times here, starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 is enough. So let's erase these. So at time 0, 3 packets arrived. So I have all these 3 packets in my queue, because this is before they are processed by the bucket. And I have 2 tokens as my starting condition. And I have, after these are processed, these tokens will remove packets 1 and 2, because it is first and first out. And I'm going to have packets 1 and 2 in my output. Right? And when the next time slot begins, I removed packets 1 and 2, so I'm left with packet 3. But there is a new arrival, packet 4, so I'm going to have that as well in my queue. And I removed both tokens, but token arrival rate is 1, so I received a new token. So I have 2 minus 2 plus 1, I have 1 token here. And that token will take packet number 3, because that came first, to the output. And I'm going to output packet 3. In the next time slot, I'm left with packet number 4, but there is also a new arrival, packet 5. So I'm going to have that in my queue as well. I removed my last token to take out packet 3, but there is a new token arriving, so I still have 1 token. And that token will remove packet number 4 to the output. I'm going to left with packet number 5, and there is a new packet arriving at t equals 3. So packet 6 is also here. I used one token. I replenished one token. So I still have one token. And that token will remove packet number 5. I'm left with packet number 6. In the next time slot, at t equals 4, no packets arriving. So I just have packet number 6 in the queue. I had one token. I spent it, but I have a new one. So I still have one token. And that token will remove packet number 6. Now on the output, I have packet number 6. In the next time slot, I am left with no packets in the queue, and there is no new arrivals, so I have nothing in here. I had one token. I spent it to remove packet number 6, but there is a new arrival, so I still have one token. That token will not be removing anything because there is nothing in the queue. In the next time slot, t equals 6, I have 2 new packets, and 8 are here. I had one token. I didn't spend any, but I added one token, so I have 2 new tokens. I have one new token, one older token. I have 2 tokens in total. And both these tokens will remove packets 7 and 8. And I am left with the arrival queue, but I have a new arrival, packets 9 and 10. 9 and 10. I spent both my tokens, but I have a new arrival, so I have one token here. And that token will remove packet number 9. I'm going to be left with packet number 10. At time 8, there is no new arrival. I spent one token, I replenished one, so I still have one, and that token will remove packet number 10. Then I'm going to left with no packets in the queue, and I'm going to have one token, and I'm going to output nothing. Okay, so this is the answer to both questions. Any questions? I'm going to publish these answers, so you don't have to take note of the answer. Just try to understand what's going on if you didn't solve it. Okay. No questions, I'm passing on to the next one. All right. Okay, so this was an exam question last year. And I think it was the most difficult question in the exam. All right, so we also have a leaky bucket here. But in addition to that leaky bucket, we have a weighted fair queuing at the output of the leaky bucket. So now we don't have an unlimited rate at the output, but we have a constraint, a rate constraint here of W packets per second. So consider a leaky bucket with a bucket size of B. So bucket can hold up to B tokens, and a token arrival rate of R tokens per second. Assume that initially the bucket is full, and the incoming traffic regularly arrives at the token wait area. So this is a token wait area. There will be some packets here, perhaps, at a constant rate of capital R packets per second. So the arrival rate of the packets, the capital R, is larger than the token arrival rate of small r. Leaky bucket is combined with the WFQ scheduler, which allocates a maximum traffic flow of W or omega W packets per second. For each of the values of the W below, plot the rate of packet flow from the weighted fair queuing scheduler over time. So we have to plot the rate of flow here at the output. Label all the key points. Assume no packets are lost or dropped at any point in the network. So that means we have an infinite queue, unlimited buffer size, in other words. that the queues of the WFQ scheduler and token wait area are initially empty. So initially, we do not have any packets here or here. Both are empty. So, in the first one, W is equal to R. So, small r, so let's first remember what the leaky buckets does. So here we do not need to remember any formulas. We don't even use anything. So we just need to think and understand how that works. So leaky bucket regulates the long-term rate of the flow by the token arrival rate here, right? But it also regulates the short-term rate by the size of its bucket. If your bucket size is too large, you can only allow that many number of packets in a very limited amount of time. And if your long-term token arrival rate is limited by R, that means your long-term average cannot exceed small r. So in the first question A, W equals R, well, R is already my long-term token arrival rate, and capital R is already larger than R, so I will always have sufficient number of packets, and over the long run, R tokens per second will pass to the WFQ scheduler, and because my output rate is also small r, which is smaller than large R, eventually I'm going to be able to push R packets per second, small r packets per second, over the network. Let's draw it straight. Okay. So my token, my leaky bucket filter here, my leaky bucket here is not constraining my output because W is already equal to my long-term average, and as long as I have enough tokens, I will be able to push these packets to the output link. Because R is equal to omega, R is equal to W, that means I have enough tokens. I will always have enough tokens to send packets at a rate of R packets per second. Right? This is very simple. So in B, now W equals capital R. So suddenly, I can push capital R packets per second here, but my leaky bucket regulates my average flow. So perhaps, yes, I can push capital R packets per second into the network for a while, but eventually, my leaky bucket will be emptied because the arrival rate of small r is smaller than my departure rate of capital R. Eventually, I will run out of tokens. And when that happens, I will have to reduce down to the token arrival rate of R tokens per second. So that means I can start sending out capital R tokens per second for a while. Bucket is emptied. I'm going to have to reduce to small r packets per second. And the moment it happens is when my leaky bucket is empty. So now let's calculate at when that event in fact happens. Let's call that time t. So let's establish one identity here. In my bucket, the initial number of tokens plus the arriving tokens should be equal to the tokens that departed when that is empty, correct? So let me write that. Let's say the initial number of tokens plus the tokens that arrive should be equal the tokens that leave when that bucket is empty. That is correct, right? I have, let's say I have 5 in here, I have 3 arriving, and when that is empty, I must have 8 that has left. So 5 plus 3 equals 8. So this is an identity I can establish and I can use to find time t. So initially, I had b tokens, right? And up to time t, I know that my departure rate is capital R. That means I remove tokens at a rate of capital R over t seconds, so I have capital R times t packets that departed my bucket. And how many in? Well, I have small r times t in, because my token arrival rate is small r, right? So let's pull out t from this identity, from this equation. T capital R minus R equals B. So t equals E minus capital R minus R. Right? Any questions? Okay. B over capital R minus R. And from there on, I will always have small r packets per second because that is my long-term average that can be supported by my leaky bucket. And my input arrival rate is capital R, so I'll have packets accumulating here to infinity. But that is not the question, so just thinking about it. Okay, so in C, W equals 0, so it gets a little bit more complicated here. W equals 0 for the first second, and W equals 2R afterwards. Assume B is much greater than capital R minus R. Okay, so for t from 0 to 1, W is 0, and for t from 1 to 2, W equals 2R. So, and after that, it is what? Okay. When t is larger than 1, W is always 2R. Okay. So now let's think one by one what happens in both of these intervals. What queues are filled, what tokens are emptied, and so on. So when we start at 0 output rate, 0 rate assigned by the WFQ, I'm going to have some packets accumulating in here, right? And I need to decide at what rate these packets accumulate here. So my arrival rate of packets is capital R packets per second, but my long-term rate is R tokens per second, but I have initially B tokens in my bucket. So I'm going to have, for the first second, I'm going to have R packets arriving, because R times 1 second is just R. And these R packets, I need to decide if these R packets will all take a token and accumulate on the right-hand queue, this WFQ queue, or for some of them, there won't be any tokens left, and they will accumulate on the left queue, the token wait area. Well, the identity here tells me that B is sufficiently large. So I can assume that there will be enough tokens for all of these packets. So at the end of t equals 1, I will have R packets all accumulating here. There will be enough tokens. And how many tokens I'm going to be left with? I'm going to be left with B minus R, because R packets remove the token, and my arrival rate is small r. I'm going to have B minus R plus R. And because this is larger than 0, established by the identity there, I still have some tokens in my bucket. So obviously, because my output rate is 0, until t equals 1, I'm going to have 0 packets per second at my output, because all the packets will be accumulating in the WFQ scheduler. So now I need to think what happens afterwards. So because I already have some packets in my queue, and my output rate from that queue is 2R, suddenly my rate will shut up to 2R. Right? This is what the question tells. My output rate is 2R, and I know that there are packets in the queue, so those packets can be very quickly pushed into the link. But I need to find the length of this interval. Let's call that delta. Okay? So I know that I'm going to have this very high rate only until my queue at the WFQ scheduler is empty. Once that is empty, I'm going to have to reduce down to the lower rate of R packets per second, because that is my long-term packet arrival rate. So after this is done, I'm going to reduce down to R. Now let's calculate the duration of that. So I will establish a very similar identity to this, but now for the WFQ's buffer, because that is that already has some packets at the end of t equals 1, and I am trying to calculate the time that is emptied. So again, the initial number of packets plus the input packets should be equal to my output packets. How many packets do I have at first? I have capital R packets. How many packets do I have as an input? Well, I still have enough tokens in my bucket because of this identity. This is indeed very, very large. So I still have R packets per second arriving. So for, sorry, not T, that is, I call that delta. So for delta duration, I will have R packets per second. So the total number of packets that are in will be R times delta. And this will be 2R times delta, because that is the rate I'm pushing packets into the link. Now let's solve this for delta. You know, this is just R delta equals R, so delta equals 1. That means this time will be t equals 2. Only for 1 second I'm going to have 2R rate. And then I reduce down to R rate. But that R rate will also not last to eternity, because my long-term average rate is regulated by the leaky bucket of rate small r. So eventually, that will cause me to drop my rate to small r. And I need to calculate the time it happens. Let's say this is delta 2, and I want to calculate this, the length of this delta 2 time, the delta 2 duration. So let me erase some of this. So I'm establishing, again, the same identity. Initial plus in should be equal to the output at the leaker bucket, because what will cause me, if you think about what will cause me to reduce my rate to small r, that is when my leaker bucket is empty. Only when that is empty, I will be constrained by my long-term token arrival rate of small r tokens per second. So again, my initial number of tokens plus my input, the tokens in, should be equal to the tokens out. But this time, it's a little bit more complicated to compute the initial number of tokens, because I had B tokens at first. For the first second until t equals 1, I remove tokens at a rate of, it's going to be complicated to compute the output rate. For the initial, I have B. Let's think about the in. For the first second, I have small r tokens arrived. For the second, I have another small r tokens arrived. And after second 2, I also have small r tokens arriving. Give me a second. 1, 2. Yes. And after second 2, I still have r tokens per second arriving for delta 2 time. So B was my initial. I added r tokens in the first second. I added another r tokens in the second. And then I added r tokens per second for delta 2 time. Yes? Between second 0, this and this. Okay, so yes, there is the output rate is 0. That's correct. But yes, but still, there are capital R packets arriving, and these packets are removing tokens from the bucket, and these packets are pushed to my weighted fair queue in here. So these packets are already removing tokens from the bucket, right? Yeah, thanks for the question. That's a good one. And let's look at my output. Okay, let's think. For the first second, again, just what we talked, we removed capital R tokens per second from the bucket. And these packets are accumulated on the right-hand side. Between seconds 1 and 2, I also have capital R tokens per second removed, because that is my arrival rate. These packets will always be served at R packets per second. So that is capital R plus capital R plus, from second 2, I still have capital R packets per second arriving. So I'm going to have delta 3 times capital R. Oh, what delta 3? It's delta 2. Okay. So now let's solve this for delta 2. Let's simplify this. B plus 2r minus 2 capital R equals delta 2 times r minus small r. So delta 2 equals b plus 2r minus 2 capital R over capital R minus R. So I can also write this as b over r minus r minus 2 times r minus r, r minus r. So this thing cancels out. So I have b over capital R minus R minus 2. So my delta 2 is b, b over R minus 1, R, b over R minus R minus 2. And if I look at this time instance, because it happens after time 2, this is b over R minus R. Same as question B, in fact. And it is expected that this is also b over R minus R, because until that time, I always removed capital R tokens per second from my bucket, and I added small r tokens per second. So in both these questions, both the arrival rate and the departure rate are the same. So it is expected that I have the same time until my bucket starts to regulate the average rate. Or in other words, my bucket is emptied. Any questions? Okay. We have some time left, but I don't want to start with the endpoint authentication because I think that's going to take us longer than 15 minutes. I will also upload the tutorial set 6, and I'll also upload the solutions to these tutorial questions. Have a look. You can attempt the last tutorial set. And this Friday is a holiday, public holiday, but we'll meet next Wednesday. Okay? And that is also when your CA2 is due. That was 12th April, right? Am I right? On when it should be Wednesday. Yeah. Yeah, also remember to submit your assignment. Okay, yeah. See you next week.